All right, everybody. Hey there. As Quackers and Cheese says, hello, everyone. And we have also some shout outs from some other folks in the chat. Courtney, Kat, good morning. Yeah, it's going to be a great stream today. We're going to talk about clustering algorithms. And let me show you actually my screen, and it'll give you a sense of what we're going to be talking about today, which is the geysers in Yosemite, or not Yosemite, Yellowstone, excuse me. So has anybody ever visited the Yellowstone National Park in America? Anybody in the chat? Or maybe you visited some other park in America, or maybe you visited a national park in your country. Tell us about it. Courtney says, I haven't, but I'm planning to. Me too. I've never been there. I would love to go, but yeah, I live here in California, and it's kind of a distance away from California. Let me actually pull up the map. I'm really curious now. America's national parks. Let's see. Okay, here they are. Wow, I found, oh, this is such a cool poster too. Hang on, I gotta show you all this. This is so cool. Oh yeah, Midwest just as far. Yeah, I know. America is a big country. Yeah, so this is what I wanted to show you all. Check this poster out. Look at that. That poster is apparently from 1938. That's almost 100 years old, this poster. How crazy is that? 80, 87 years old. 80, yeah, something like that. Something like 87 years old. But yeah, I love Yellowstone. I would love to go there, and I guess this is all of the national parks of the United States. So here's my house in California, and here's the Midwest that Courtney was mentioning. This is the Midwest, so we're pretty far away from Yellowstone, which is this big park over here. But that's what we're going to be talking about today. We're gonna do some interesting exploration of Yellowstone. But before we do that, I want to get us all checked in. I'm realizing I didn't send this out ahead of time. So let me send it out right now. It's going to be the check-in link for today. Yeah, because you're going to really definitely want that. Hi there. Welcome to the stream. And there's our check-in link. So go ahead and click on this check-in link whenever you're able to, whenever you're ready for that. And I'm just gonna put up this slide that I made. Isn't that a cute worm? Does anybody know? Can anybody tell me what that worm is? I've been using AI to try and make my own graphics. Okay, the mascot for the season. Yeah, so that's right, Quackers. Yeah. Hiya there, VoIP. Good to see you. Yeah, this is our season mascot. So I was able to make this with AI just by showing it the sticker that we have for the season. Izzy, yep, Izzy the inchworm. That's right. That's our mascot for this season. But yeah, just go ahead and check in. It's really important. I'll tell you why. There's really two main reasons why. First one, super important. We want to get you. We want to get you that swag, right? So we give out swag to people who attend Global Hack Week. It could be stickers. In the past, we've given out T-shirts and other swag. But to get that, you need to check into events. Second reason, we want to know what you're interested in. We want to see, what times of the day are people loving to go to streams, what topics. So please check in. It really helps us out. A hornworm. Never heard of a hornworm, actually. Let me check. Let me research that. Oh, wow. That is a cool looking thing. Let me show you all this hornworm. I've never seen a hornworm before in my life. Here it is. I hope this doesn't scare anybody who's afraid of bugs. But there it is, hornworm. But no, it's not a hornworm. Yeah. Oh, he's surprised to be a mascot. Yeah, that's right. Yeah, no, that's funny. I wanted to have his mouth open to say something. That was my goal. But yeah, so hopefully you're all able to check in now. I'll just put the link up one more time while we go through this next bit of the slides. But yeah, definitely check in for the event. Okay, so this is our Old Faithful geyser, and actually I'm gonna play this video for all of you so you can get a sense of what we're gonna be looking at today, all right? So let me make sure it's actually playing audio too. Yeah, it is. All right, so I'm gonna turn down our music. Push play on this and let me know if
normally go on vacation, they have a schedule that they use. So we're going to have lunch at noon or 1 o'clock. We're going to go scuba diving at 3 o'clock. And we're able to use the clock to base our activities on. But here at Old Faithful, we don't use the regular 12-hour clock that everyone else uses. It's all about Old Faithful. So when people choose to have their lunch or their dinner or their nap or their walk through the geyser basin, all is based on when the Old Faithful is going to erupt, so they can be sure and see it. Old Faithful is getting ready to erupt, so I am trying to time it. Oh, and there it goes. So I'm hitting the stopwatch, and I'm noting the time on the atomic clock at 12:58, which is pretty good considering that the prediction was 12:59. So we're getting closer and closer. Now I'm going to measure Old Faithful. So as the plume of water gets higher and higher in the window, I'm comparing it to this tree right over here. And I'm using this picture, which has a triangulation setup, to identify how high the water went on the tree. And what I figured out, Old Faithful's hit its peak already, was that it came to about right here, which is about 140 feet. So in the logbook, in addition to the start time, I'm going to record 140 as the height of this Old Faithful, which is the tallest one today, which is kind of nice. And then all I need to do is keep an eye on the timer and see how long Old Faithful lasts. And that's all going to determine how we predict the next one. I'm also going to record the interval between the last Old Faithful and this one, which is 89 minutes. We take those intervals and we use those to make our average. Basically, we use observational Old Faithful to figure out how to predict it. And it changes through time. Just a couple weeks ago, we were using 88 minutes for a long eruption. And now we're using 90 minutes because we figured out that that was going to give us the better average. So Old Faithful is now been going for 1 minute 48 seconds. It's still going strong. If it lasts longer than 3.5 minutes, then we have what we call a long eruption, which is the most frequent form of Old Faithful eruptions. It's a bimodal geyser. It has longs and it has shorts. If it's going to have a short, I would expect that any minute now, it would just suddenly stop. If it were to do that, I would go ahead and predict it for 62 minutes, but it looks to me like it's probably going to be a long. Still a lot of water coming out of it. We're at 2.5 minutes now. So we're going to wait another minute and make sure that Old Faithful is a true long. We're getting to the point where the water's pretty low right now. So I'm going to be using the binoculars to determine the difference between the water and the steam. We won't consider the eruption done until there's no more water coming out. So we're still getting kind of big spurts of water coming out of Old Faithful. Most of the people have turned away now. And we are at 3.5 minutes. So we're going to consider this to be a long eruption, but I am going to wait and record. Okay, and it's done. So 3 minutes, 42 seconds. So our start time was 12:58. So our next prediction would be go 1:58 and then go to 2:28. I'll write 2:28 in the book. And then the next thing I have to do is tell the world. This is 724 Victor with the Old Faithful prediction. Old Faithful Geyser is predicted to erupt at 2:28 p.m. plus or minus 10 minutes.
Okay, everybody. So, what did you think of that? Old Faithful Geyser, interesting subject, right? Yeah. So, let's go ahead and continue along. I want to play it again. And I'm going to just show you this link here, which is exactly what she's talking about. So have a look at this real quick, and I'll send the link in the chat too. Let's see what we can learn about this. Okay, so yeah, neat stuff. An Earth clock. Yeah, it is kind of cool, right? That we have this Earth clock. And then Courtney says, "How crazy how close the predictions get." Yeah, I know. I'm amazed that we can actually get a good prediction out of this system, which seems to be random. I mean, you would think the eruption might be random, but actually no. But yeah, so here it is. Here's the current eruptions for today. So it's actually April 15th. Let's zoom in a little bit. Maybe it'll help us a little bit. There we go. So we've Old Faithful here. We had one observation at, holy cow, this would be midnight basically. Another one at 2 a.m., another at 3:30, and another at 6:30 a.m. And that's the current time the current time over there would be, I guess, 7:15. So they're already observing these rangers all night long. Isn't that kind of cool? By moonlight, right? Wouldn't that be sick to see one of these by moonlight? Yeah, that would be awesome. Our video is in the day, so we don't get to see that. But yeah, so okay, so I sent that link in the chat. You all can check that out, and maybe if you've ever visited Old Faithful, you can have a look. But I want to actually talk to you all about what is a term called a bimodal distribution. You'll notice in that website we were seeing some shorts and some longs. Okay, and so bimodal means that you have two main groups of data, and there might be some overlap. So you see there's a small amount of overlap between these two humps. Where you're like, is it a short? Is it a long? I'm not sure. But in reality, most events are either clearly a short or clearly a long eruption. And I did find this link talking about the possible cause, maybe, of this eruption. So they say that there is a chamber. Let's zoom in here. That stores the water and actually lets them predict with more regularity these eruptions. So that could be kind of an interesting thing to look at if you're interested in science and things like that. that could be a reason why. Maybe we're seeing these very timely eruptions. But now I want to actually approach this from a machine learning perspective. So we're going to actually approach this from machine learning, and I'm going to talk a little bit about classification, okay? Because you might remember what the park ranger is doing is they're actually looking at the eruption and they're saying, oh, this is a short eruption, or they're saying, oh, this is a long eruption. And what they're doing is classifying those eruptions based on a type, right? So we have many different classification algorithms. I've put many of them on this page here. And actually, number 6, if you look at number 6 on this page, it's actually a clustering algorithm. So we call this k-means clustering. And so clustering is a little bit different than a typical classification. But let's talk about the classification algorithms first. So for example, we could have a fruit classification algorithm. All right, so here we have 3 fruits on the left. And maybe we have data about these fruits. So maybe we know about their color and their size and their weight, for example. You can see these 3 fruits, they differ in all of those categories, actually. And so when you pass them into the classification algorithm, the idea is that the classification algorithm could use these features to sort them into 3 categories. All right. And so here's another example of a classification algorithm, which could be used for decision making. So let's say that you want to know whether you should go out for grocery shopping or you should stay home at your house. Well, we have some features that we could use for that. We could talk about the time of day. We could talk about the traffic levels outside, whether there's a lot of traffic on the roads or in the trains, and whether there's food in the fridge. And then also how hungry you might be might dictate whether you go grocery shopping or you stay home. So you could think of the classification algorithm here as kind of like your brain telling you, oh, let's go to grocery shop, or maybe we should stay home this time. And then finally, I wanted to talk about one last example, which could be email spam. So email spam is going to take raw data, such as the spam filter, such as the sender of the message, the time it was sent, the subject, and the body of the message. And it uses those features to determine whether it believes the message to be genuine or not, or in other words, spam or not. And then it'll move that to your inbox accordingly. Right? So these are just a few examples. And now I want to cover, how do we construct an algorithm specific to our needs? So we could start by talking about the type of learning. So there's 2 major types of learning. There's supervised, and in a supervised learning context, models will learn from training examples provided by humans. So let's think about the video we just watched. The woman who is recording the time of eruption, the length of eruption, and then she'll say, oh, yeah, this is a long eruption, or this is a short eruption. Think about our website, the geysertimes.org, right? Look at this. These data are being told by the park ranger, someone named Joe, who's saying this is a long and this is, I guess, a short. So if it's long, they'll say long. If it's not, they'll say just WC. Right? So those are some examples of supervised training. And it's mostly used for discrimination tasks. And what that means is not what you might think of discrimination in a bad way. It actually is more about recognition tasks. So it means to recognize, and in other words, you have 2 things and you want to discriminate against them and make sure that they are recognized as different, right? So these 2 eruptions could be recognized as one being short, one being long, right? And that difference. And then here we use training and testing data. So what that means is that we learn with the model from the training examples, but we need to make sure that our model works on data that it has not seen yet. So for example, testing data, right? So testing data would be, okay, we're going to leave a few samples out of the box, call it out of the box sampling, and we're going to see how our model performs on those. Typically, we use an 80-20 split here. So if you had a 100 eruption data set, you would use 80 of those for training and leave 20 of them for testing. And so here's an example of, I'll actually show you that. I have a lecture where we might discuss that at the end. Okay, so wanted to talk to you about unsupervised learning. But before I do, let me answer this question in the chat. By VoIP says, I wonder why they don't use more accurate methods to measure these eruptions. Yeah, me too. Maybe it's just their tradition, they have these like park rangers, and yeah, the park rangers like to tell the guests about what eruption is going to happen when or something like that. I don't know. It's a good point though. But yeah, for unsupervised, we have a little bit of a different situation. So unsupervised models will learn from unlabeled data. Okay. They're mostly used for quote unquote generative tasks. So it means a task that it's kind of, I could call it an imagination task where you're actually trying to conjure up new data. But in an unsupervised learning scheme, this is very important. There's no split between training and testing data. So all of the data is used for unsupervised. Okay, so at the end, we will look at k-means clustering algorithms in Python. And that's what we're going to actually do today. This is technically a clustering algorithm, but it does classify data into categories. So yeah, there you go. And here's an example of one of these clustering algorithms, one of these unsupervised learning algorithms. It's called a GAN, or a generative adversarial network. And a GAN actually is going to use parameters like age, eyes, perspective, and mood, in this case, to generate a picture of a person. And you basically can't distinguish between this person and a real person, which is kind of the point of generative AI. Pretty cool, huh? Okay, so now we're going to do a type of learning called reinforcement learning. And we actually have a lecture on this later in the day. Let me post the link to that. So if anybody here is interested in reinforcement learning, you can join for that. Let me send you all the link in the chat. This is the link for registering for our reinforcement workshop. So if you're interested in reinforcement learning, definitely take a look. But it's basically where the model learns the best strategy using a scenario given by humans. And so the scenario is composed of two parts: actions plus the environment. So actions would be, let's say you're playing Monopoly. Action could be rolling the dice and choosing like what to buy, right? Maybe you buy something in Monopoly or not. Environment is, all of those other parameters around you. So in Monopoly, you have, the environment of the other players moving around, the scene, all the different buildings getting built. So that would be an example of an environment. And then this is mostly used for decision-making tasks. So one example is robotics. We're actually seeing now a lot of reinforcement learning done by in order to fine tune large language models. So when OpenAI, ChatGPT, when they come out with a new model, they'll have humans actually fine tune that model, make sure it works really well for human purposes. And they use reinforcement learning to do that. So the model can learn how to essentially how to make a good response. And an example is Markov decision process. So this is actually this lecture that we're going to discuss later today or tomorrow, depending on your time zone. So yeah, have a look at this. Have a look at this over here to get that. Okay. Oh, good point. Courtney says maybe the consistency of their method keeps it accurate. Yeah, that's a really good point because if you think about it, these park rangers, they might not necessarily want to change to a new instrument or a new method because they have that tree method that they use, right? So yeah, if they change to a new one, it could change their data. Really good observation. But yeah, there's some really cool stuff on Markov decision processing here. You can have a look at this lecture from YouTube by Computer File, which is an amazing YouTube channel about computer science. I don't know if any of you have heard of this channel, but I'm going to paste a link in the chat to this video so that if you want to learn more about it, you can. Yeah, Voight says, so we would use reinforcement learning to solve the trolley problem. Now that's interesting. Yeah, I suppose so, because in the trolley problem, you have a scenario, right? You have a scenario that you have actions to choose, environment. You just need a reward function too. So that's actually one of the things I didn't mention here is you need a reward function to tell the algorithm how much reward it gets for ending up in certain situations. So for example, if you wanted to do the trolley problem, we have, let's say, one person on one train track and three people on the other train track, and you're trying to minimize the amount of people on the track, right? So the reward would be 1 or 3, and so you're going to minimize that. But yeah, good point. Of course, the trolley problem, those two the weights are equal there, so I don't think you could really solve it, but you could certainly try. Okay, so I just wanted to show this Venn diagram, which kind of illustrates really the different types of learning and how they relate to different tasks. So on the left circle here, you have unsupervised learning. So for example, imagine a picture, generate a video, um, write some creative writing. That's all unsupervised. Then on the right-hand side, firmly on that right circle, we have recognize images, analyze sentiments. And then in the middle, we would have describe an image or maybe translate a language. So these are just some of the ways that we can look at some applications for these learning. Here's some other features to consider when you're making when you're choosing a machine learning model. So we had those 8 that we had at the beginning. How many variables do you have, right? So if you have more features, or less features, you might be better suited for different models. So on the left, we have what's called a support vector machine model, where we can actually draw basically a plane that divides the data according to some equation and minimizes the distance, weighted distance from this plane. And then on the right, we have maybe a decision tree algorithm, which is another type of algorithm that makes decisions based on a certain threshold and sorts the data into boxes. And then another factor is your relationship linear. So if it is, you might consider a linear regression model, which a lot of people don't realize that's a form of machine learning. And if it's nonlinear, you might rather consider a decision tree. Okay. Another one to talk about is how much data do you have and how fast is your computer? So, we're actually reaching, this is always a problem in computer science, and we're reaching limits now because, we have these huge computers and NVIDIA. The reason why NVIDIA has become such a popular company is because they can make these mega GPUs called H100s, and they're always coming out with new ones that can speed up your algorithm processing time. But training a single model now can take for some of these biggest models, these biggest machine learning models, it can even take billions of dollars, literally billions. Of course, we're not going to do anything that involved, that intense, so we don't need to worry about this. But definitely something to consider as you go through your model selection. And I'll say that the number of parameters is also very important. So, how much flexibility do you want in your training, right? So if you want to have a lot of hyperparameters or not. And we're actually going to use this one here, k-means clustering, for the first portion here, k-means clustering, because yeah, I think we can probably try to get this done with k-means clustering, this eruption data set. Okay, so very tiny mini break here, tiny 1 minute break, and then we'll do some k-means clustering. So this is literally just to reorient ourselves. Any questions anybody might have? Yeah, lots of new words, says Voiv. Yeah, there's a lot of stuff here that we covered. That's why I don't want to spend so much time on this. I want to keep most of our time for actually implementing some of this stuff. I'm gonna try something new today too. So the first part we're gonna do is actually like something we've already done before, where I actually have written out the entire script, and then we'll just copy and paste it in. But then the next part here, the next half, we're gonna actually build our own, okay? So yeah, that'll be cool. Okay, let's go on to k-means clustering. So this is where we're gonna get actually hands-on with this, okay? So k-means clustering is an algorithm. It's a clustering algorithm, and again, we're sorting into groups. So you could call this somewhat of a classification algorithm. And if you notice, it's randomly initialized, which means that the answer will be slightly different each time. So we put these points into random parts of the field, and then over time they might evolve to minimize the squared errors from a centroid. Okay, so centroid would be one of these X's, these black X's, and you can see in both of these cases, in the first side and the second side, which side, first side or second side, has less squared errors. Maybe just think about it visually, and then also if you look at the top, there's an SSE. It shows SSE. So tell me, which one do you think, left or right? Does anybody know what the which one of these might be true? Yeah, exactly. VoIP says right, exactly right. So in that second one, we have a better clustering here. You can see on the first side, actually, red and blue are kind of together. There's no separation between them. So yeah, it kind of makes sense. Okay, so here's a few assumptions of the k-means clustering algorithm. First, the first assumption, of course, is that there are k clusters. So, you know, this is kind of like, you already know how many clusters there should be. Now, with our eruption data set, you know, our rangers, our park rangers told us that, you know, there are long eruptions and there are short eruptions. So we kind of already know that there should be just two kinds. And then the features should be isotropically distributed. So that means that it, you know, essentially these features should be not related to one another. So we're going to have two features for our eruptions. We're going to have the length of the eruption and the time in between eruptions. And those two features should be not related to each other. And then each feature has a spherical variance. So what that means is that it looks a lot more like this top left panel here, and not a lot like this top right panel, which is definitely not spherical. You want them to look a lot like blobs. And there is some flexibility in many of these assumptions. So if you wanted to look into this in more detail, you could click the link. But yeah, just know for now, we're looking for something that looks a lot like the top left corner, where we kind of already can tell, okay, maybe there's 3 blobs, and we're just trying to build an algorithm that can easily classify them. All right, so here is our analysis on the geyser. I'm going to paste this into the chat so that you can all see it. It's a GitHub link. If you click on it, it should bring you to my GitHub. And there's a PDF here, which has some of the slides from an older workshop that I did. It should be very similar though. And then what you're going to want is lesson 1 blank. Okay, this is our blank sheet. Oh, it's not so blank. Okay, hang on. Give me a minute. I'm going to try and pull this up and blankify that. Let's see here. All right, just give me a minute. I'm gonna try to blankify this a little bit for us. But yeah, while we're waiting, if anybody has a question about any of this, really, let me know. I'd love to hear from you about it, and if you want to chat about what you're struggling to understand, or maybe there's just something that yeah, you want more clarity on. Okay, I'm getting hooked up with the okay, so I think I now have this working. I'm gonna just update this for you all. Okay, it should be blank now. So if you go now, I'm gonna refresh this a little bit here, refresh the page. And when we click on lesson 1 blank, this is now a blank workshop, okay? So you can now use this, and lesson 1 itself has a bit of somewhat of an answer key. So I would not recommend looking at that yet, but we're gonna do this blank so that we can actually get it. Okay, how do we decide which method was the best for the classification of data? Yeah, I know, this is a really tricky one. To be honest, the best way to do it is to try a bunch of them and see which one works best. I hate to say it, but that's so much work. So that's why I tried to give you all some of those hints from those slides. Is your data linear? Is it nonlinear? Do you have a lot of different features? Do you have a few limited number of features? That's kind of going to drive some of these decisions. So feel free to reference that worksheet I gave you to try and make sense of this a little bit and narrow down your choices. But yeah, unfortunately, the best way is to really just see what method is best, right? By actually doing it. And then another question, how would someone be shown the results on this stuff? Would it be screenshots of the outcome, or would it be put on a dashboard of some sort? I'm glad you asked about that. So actually, we might try to make a dashboard today, but I know for a fact that in our TyPy workshop, which is on the 16th, which is tomorrow, we're going to actually implement a dashboard with the results that we get from today's workshop. So this is for tomorrow, okay? And if you're interested in making a dashboard, we're going to learn how to do that using a library called TyPy in Python. So that's a great question, and but today we're just going to make some plots to show the outputs. Okay. Yeah, no problem. Thanks for the question. And then Kartik says, in K clustering, we're basically updating the centroids to minimize the distance between the points, right? That's exactly right. So I actually think I had some example. Okay, let's see. I had it up for all of you. It was on realpython.com. Oh yeah, so let me show you from their website. You can see how it actually works in practice. So there's the start, and if you look at the SSE, which is the standardized squared errors, standard square errors, they go down after each iteration. So the iterations are on the very top. You see 1, 2, 3, 4, 5. And the SSEs are slowly going down in each case. And the centroids, these black X's, they move accordingly, right? And it does seem like the initialization on the right was much better. Remember that the initializations can really influence your outcome. So that definitely gave us some nice clusters. But in both cases, we're getting separation of these three clusters. So great question on that. Great questions, everybody. This is really fun. I love to hear it. Okay, so does everybody here? Let me know. Oh, okay. On the left, how are the clusters decided? Okay, let's just answer this one question before we continue. So they're decided in the same way as the right, but if you notice, every iteration, the X's, they stop moving less and less, right? So the yellow X immediately moves here and then barely shifts, right? Same with the red X. Moves a lot the first time, then it barely changes. So this is a really common problem in machine learning, and it's called a local optimization. So in both of these cases, the machine learning model thinks that it's found the best solution, and it just kind of settles into that. So let me give you an example. I'll show you a picture. Okay. Here's an example of a global versus local maximization that I found from the internet here. Okay, hard to use this person's website, but Here it is. So you can see global maximum is actually, or here's the lowest point right here, this red point, global minimum. This is what we're interested in. But sometimes the machine learning model will get stuck in a local minimum, where it thinks it's found the lowest point, but it hasn't really found it. And so that's what's happening on the left here, is it's actually thinks it's found the best solution, but there's even a better one that exists on the right. So this is a really common problem in machine learning. The best way to resolve this is to reinitialize your algorithm, which is why they do a second initialization here. And if you test a lot of different initializations, which we will do for this k-means clustering, and you always get a similar answer, it means that you've got a great global, you're more likely to have a global minimum, not just a local minimum. So hopefully that helps with that. But yeah, let's see. What I was looking at was the GitHub here, and it's now blank. So go ahead and download this Python notebook. Now, is anyone in the chat unfamiliar with Python notebooks? Let me know, because if not, then I'm going to actually open this up in Visual Studio Code. You can download this whole lesson by actually going to lesson 1. And I think if you click up here, oh, no, that didn't work. Oh yeah, so if you go to the home page here and you just click download zip, you can do that. If you are familiar with GitHub and you want to actually open it up in your Visual Studio Code on your computer through cloning a repository, that's good too. But yeah, we'll click download zip here. And when you do that, you can open up lesson 1. So let me show you what that looks like when you open it up on your computer. So I have it open on mine now. Okay, here we go. Sorry, everyone, I'm just taking a minute to get this set up for us. All right. That looks like it's working now. So I have our clustering algorithm tutorial set up here. I guess I left a little something in there. Sorry about that. But yeah, the first thing we're going to do now is, because nobody mentioned that they want help opening up a Python notebook. So what I'm going to take that to mean is we're not going to spend any time discussing how I got from that website that we were just on to here, which is my code editor where I can type and we can work on this code. But if somebody later decides they want some help with this, we can go back and we can show how to do this. But we're going to just for now assume that we're here in the notebook. Yeah, it could open in PyCharm. I believe, let me see. Yeah, Jupyter Notebooks will open in PyCharm. So good question. And so as long as you open this up in your computer, just download that zip file, extract the data, and then you can open in PyCharm. No problem. So, all right, let's get started then. So I'm going to actually start by doing some importing of necessary libraries. And oh, please show us how you did that so quickly. Okay, yeah. So let's actually talk about this for a little bit. Okay. So when we go into GitHub, okay, stop my screen. Who here has any kind of IDE, whether it's your PyCharm or it's Visual Studio Code? Who has one? Does anybody not have an IDE, or they don't know what that is? because I'll send you a link to a great IDE that I like called Visual Studio Code. Just sent it in the chat, and I'll show you where you can find it. So it's on this website here, and you can just click download. And you should be able to install that Visual Studio Code editor. And then you'll open it up. And it should look like this. So I'm just gonna open up a new window of Visual Studio Code to show you what it might look like. Okay, so looks like you have both PyCharm and VS Code. That's great to know. So what you'll do is, once you have this open, right, you want to actually click Clone Git Repository, which will clone a remote repository into the folder, and you'll click Clone from GitHub. Once you do that, and the repository name is Cropper S/MLH Classification Workshop. So I'll put that in the slides here, or in the live stream. So that's the name of the repository. And once you do that, it'll open up. It'll open up this this classification workshop, and that's what I had open before. All right, so let me try to actually get that open again, because I had it open a minute ago. So I'll just try to open it again. Okay, so just a quick tutorial on your editor here. On the left panel here, we have all of the files and information that we need. So this is actually the slides, if you want to check them out. A little older version of them. I should update it actually for today's workshop. But then we have our clustering algorithm. So that'll be right here. And in lesson 1 blank. So definitely keep lesson 1 blank available for yourself. Okay. So I'm going to actually get started now, because you know, I've given a little bit of time for you to catch up here. Hopefully that's been helpful to you all. Because sometimes I go a little too fast, so I apologize for that. That sometimes I go a little too fast. But hopefully we're back up and running. So first, let's import libraries, okay? And so we're going to use these statements import. So we'll import pandas, which is a data frame library. We'll import NumPy. We'll import matplotlib, which is a Python data visualizer package. And we're going to import what we call from sklearn, which is a machine learning package, .cluster, which is our clustering algorithms. We'll import k-means, okay, which is our k-means clustering package. And we'll run this by clicking in this top left here. It might ask you to run through Python, so you might have to install some Python or attach some Python kernel. But you know you've got it right when you push the green, when you get a green check mark. Okay. So we have this this idea to implement clustering on this, and there's actually a post on rposts.com where they do this for R programming language. So that's why we've adapted it, changed it a little bit around, but we're also doing it for not for R, but for our workshop, so for Python. So we're going to read in the data. So read in the data. And the way we're going to do it is, if you look in this top left panel, we actually have a folder called data. And there's a CSV called faithful.csv. If you open this, it actually has a lot of data. So each of these rows here is an eruption, and it's in minutes. So this is in units of minutes, and so is waiting. So eruption measures the amount of time that the geyser spent erupting. So this first eruption was 3.6 minutes long. And let me actually zoom a little bit for this so that you all can see a little better. Hopefully that's a little bit better. So 3.6 minutes, and then 79 minutes in between from the previous eruption. And then the second one has 1.8 minute length eruption, 54 minutes in between. So you're starting to get a sense of the patterns here, right? So now we can go to this this standard k-means clustering example here, and let's try to read in the data. So I'm going to say df equals pd.read.csv, and we'll first start with data, which is the folder, and we're going to put faithful.csv. And what this is going to do is read in the data. So now we're just going to do df at the end to visualize, and we'll click run. Okay, so I've run this, and now all the data is loaded into a table object. So we can actually use this table. It has 2 headers on it, and it has 271 entries, okay? So the purpose of this is to take the data from a file, like a CSV, and put it into a variable in Python that we can actually use. So we want to visualize this a little bit more, actually. I'm going to try that. And first I'm going to do some histograms, actually, which is not in the answer key, but I want to just try this out. So yeah, let's try a histogram for weighting, which is one of the variables, okay? And you can see I'm selecting weighting using this hard brackets form here, right? So let's click run. You can see. And does anybody recognize this? What is this distribution here? Do you recognize it from our slides? Remember Izzy the inchworm and those slides up at the beginning. Okay, nobody has a guess, so I'll just tell you it's called bimodal. Okay, so this is what we call bimodal. Yeah, that's all right. And so if we look at the eruptions, let's look at eruptions too. Oh, it's actually called the eruption, not eruptions. Okay. Look, also very bimodal, right? So we can kind of start to see you know, what this looks like. I'm actually going to then have a new cell where we just where we plot the scatter plot of these data to show a little bit better. Eruption and weighting variables at the same time. And I'm going to give it some title to this called Fateful Eruption Dataset, and some X label, which will be the eruption time in minutes. I'll call it the eruption length in minutes. And also the waiting time between eruptions, also in minutes. And so when we run that, here's the plot we get. And you can see, you can already kind of tell, right, the clustering is starting to happen. There's a big concentration of events up here where there's long eruptions with long wait times. There's also a big cluster of events at the bottom left where you're using shorter eruption length, shorter wait time, but there's plenty of events in the middle too. And so, how would we classify one of these, right? How would we say, oh, this is a long eruption, this is a short eruption? How would we do that? We're going to use this algorithm. And so the first thing we're going to do to implement this in the algorithm is format the data to be useful to the k-means model. And so the way we do that is we're going to do x equals df dot values. And so when we do this and we type x, you can see that the data actually comes in this array format. Okay, so each of the events are a single array with a first and a second feature, which is eruption length and waiting time. Okay, so the next thing we're going to do is build our k-means model. Okay, so first we'll say k-means, and the first variable we'll put into this this k-means object that we're building, which is one of our clustering models. The first object we'll put in is called n clusters, and we'll put in equals 2, okay? Because we're pretty sure this is a bimodal distribution. And then I'm going to choose init equals random. So remember, those initializations can have a big influence on our final results. So we're going to use a random initialization to remove any kind of influence that we might have already over the process. And then if we always get to the exact same place with this random initialization or pretty close, then we'll be having, we'll know we're pretty confident in our clustering. And then finally, there's this variable called max iter, which is maximum iterations. So I just have it set to 300 right now. You can pretty much set that to whatever you want. But it just means that if after 300 adjustments of these centroids, the model's still not sure that it's converged, let's just stop playing with the centroids and return the result. So we are never going to get to 300 with this data set because it's pretty small and it also has already pretty well-defined clustering. But just thought I would define that so that you can see what that parameter looks like. And these are actually called hyperparameters. So you remember we had that slide about, if you have like more parameters or less parameters to tune. So we can tune a lot of these parameters: initialization, cluster number, maximum iteration, to fine tune our model. Oh, and a question: can you show the histogram code section really quick? Yeah, sure. So here's what we did for this scatter plot, and I'll make the histograms too. This is how you do the histograms. You literally just type the word plt.hist and then the variable you want, and then plot. So I'll just put them, not generate. Let's put them down here. And you can add some titles to them, some axes on them by just copying this code and pasting it, if you want to play with that. Oh, okay, didn't change to scatter, right? Okay, sounds good. So now you have some practice with all of those. And let's try and now actually fit our model. So the way we fit k-means is by typing k-means dot fit, and then we will add as an argument to this method x, which is the data, if you remember, that we put up here, df.values. So the fit method will fit the k-means model to the data. Okay, so when we run this now, it runs and we get this output here, which says k-means. Okay, so this is our object that we just created, which is great. Okay, so let's see. Oh, I'm just going to delete this cell here. Well, what was the result of our fit, you might ask? Well, I'm going to delete this cell too. I don't want to give away any answers. Okay, so here's how we can know about the results of our fit. So we have this k-means object now, right? We can actually investigate its properties. So one way we can investigate it is by looking at the cluster centers. Okay, so the k-means cluster centers is one of the attributes of this k-means object. So we can actually use this cluster centers attribute, and it's got 2 in its list of cluster centers. So let's just print this and see what it looks like. Yeah, so there they are, the cluster centers. Let's actually print them out one by one because it's kind of hard to see them this way. So you just do cluster center 1, and remember the first element of the list in Python is actually element 0. The second is element 1, and so on. So when we print them out like this, we see that the first cluster center here was 2 minutes of eruption and a 54-minute waiting period. And then the second cluster here is a 4-minute eruption and an 80-minute waiting period. Let's actually look at our geyser.org geyser times and see, does this make sense to us? Let's stop the screen and check that out. So we had our geyser times. And okay, so let's refresh, all right? Okay, so we refreshed and you can see we actually got another eruption here. So let's see here. And the long eruption at 6:22. And then it was another, how many minutes is this? 100, approximately 100 minutes until the next eruption. About, let's say about 90 minutes until the next eruption. So it kind of makes sense, right? That this would be approximately right. Okay. So let's actually go back to our code because we have a little bit more to work on here. Okay. So what I want to do next is print out the standard squared errors. And this is what we call the inertia. Okay. And so if we run this code, we see that the inertia is 8901 of the data set. So if we were to rerun this code, let's rerun, because remember, this is randomly initialized. So I'm actually going to make a, let's make a loop with this, okay? And this is something that's not in the answer key, but I just want to see. So this was our original inertia. So I want to test, let's test how initialization impacts inertia. So I'm going to let AI actually fill this in for me a little bit here. So isn't that kind of cool? And I'll show you, I'm actually going to show you all this Copilot thing, which I'm using. We're going to look at that a little bit. But let's say we want to run this 20 times. So we're going to do 20 different experiments where we initialize a k-means model at a random location, and then we fit it to the same data each time, right? So we're always fitting to this X data. And then we're going to store the inertia in this, and then we can do let's do a histogram. Actually, I want to do a histogram of the inertia. Okay. Okay. So we run this, and it looks like we almost always get an inertia that's pretty close to 8,900. There was one time where we got this inertia 8,980, but almost always we got 8,900, and that matches with our original value. So we're pretty sure that this is the best that the model can do. Now, if we saw that 8,900 was here, and then there was a bunch of points to the left of this where the inertias were quite a bit lower, that would be implying that we could do a lot better. Let's actually change this to, let's say, 2,000. I wonder how long that'll take. Hope it won't take too long for our, well, let's just see how that runs. Okay, so the next thing that we'll do is I want to print the number of iterations that it took to actually run this. Okay. Oh, let's actually make a new cell here. That's taking too long. I don't like that. Let's try 200 instead of 2,000. Right? And I'm going to make a new code cell too. All right, so here's our 200. And actually, there are a few at 8,905. But it really does seem like we did the best we could at 8,901. So this is a really good way to double check your work. Okay. Now we're going to look at the flags. So this is actually going to tell us what the individual data are labeled as. So remember, in classification, we're always interested in labeling our data. So when we print out these labels, we see 0, 1, 0, so on. And if we match these up with our X data, like for example, this first eruption is classified as a cluster 0 eruption, which if you remember, that's those short eruptions. Or I'm sorry, those are the long eruptions, I guess. Cluster 1 is a short one, right? And then a long one, and then a short one. You can kind of go along and see how they match up. Okay. And so to plot these, and this was one of the questions earlier, how would someone be shown results on this stuff? Would it be the outcome in a dashboard or some screenshot? Here's what we're going to do. That's what we're going to do now. So what I'll do is first I'm going to say category 0. And category 0 we're going to label as our data frame, but we're going to filter out the data frame so that we only keep eruption data that is for flags equals 0. Okay, so here's our flag. So this is going to mask everything that's not a 0 out of category 1. So if we print now category 0, we'll delete this here. Oh, somehow I printed this out as a markdown, not a code. I hate it when that happens. So here's the category 0 data, and I'm going to do the same thing for category 1. And then we can plot them. So I'll plot category 0, category 1. We could even plot the cluster centers if we want. And let's run it now. Okay. So here is our, oh, I don't know what that means. But anyway, so here is our data. And you can see that we have, on the one hand, I want to plot these a little bit, looking a little bit more like our example here. So we'll use these little X markers. Yep, and I'm going to use, I think we use blue and orange or something like that for, whoa. Yeah, so this is more about what it, what it looked like before. So you can see that we have a really clear clustering behavior, which we already kind of could see with our own eyes. But now we're actually able to visualize it. And so the cluster centers are plotted, and what these cluster centered positions are determined by is actually the weighted distance of all of the points in that cluster. So they're minimizing that weighted distance. Okay, and so then we have this question here, this quiz question, that now we imagine that we see a new eruption, right? And this one is going to last for 3 minutes. And let's say it came 75 minutes after the previous one. So what category would you place this eruption in? Well, you could pretty feasibly do this by just using k-means.predict. And so we use the following to do that. We just use the predict method, and we have to pass in some data here. So we're going to pass in data just like in the same format as the x variable, where we had a list of lists. That's how we predict for k-means too. So when we run this, we expect it to give us 0. So there's 0. So let's actually try to plot that on this same graph here. So I'm just going to copy the code here. I'm going to paste it down here. And I'm going to add a new scatter where we plot this one. And it's saying that this is going to go into the 0 cluster. And let's see if that looks right to us. All right, so there's the red new point. You can see it's pretty ambiguous, honestly. If you were, if you were trying to do this with your own eyes and you weren't trying to necessarily use an algorithm, it would be pretty difficult, right, to actually tell which one this would be. But in this case, we're able to pretty easily classify it using our model. Okay. So next, a non-spherical clustering example. And let me delete this. I don't like the fact that all these cells saved. Go away. Go away. Okay, save that. And this is where we're going to try to break those assumptions of the k-means clustering algorithm a little bit, right? Because if you recall, let's actually go back to that assumption slide, so that you all can see what assumptions we had. Here it was, right? Oh, wrong. Okay, there we go. Let's check the assumptions for k-means clustering. Oh, actually it's, here it is. So we had some assumptions here, and one of the assumptions was that each feature has a spherical variance, okay? And that they're isotropically distributed, so that, basically we see little blobs, right? The features are blobs. Now, when we look at something that's not a blob, the clustering algorithms will break down, okay? So let's have one more look at this clustering stuff, and we're going to look at something called bullseye. Okay, and just putting this up for my own reference here. Okay, so we go into this Visual Studio Code editor, and we'll type read CSV, and we're gonna use a new data set, which I call bullseye.csv. So what I want you to imagine this is, and I actually use this to just get X and Y out of this bullseye CSV. What I want you to imagine these as is, imagine you're playing darts with your friends on a bullseye. And these are the positions of each of the darts. So we get X and Y positions of the darts. And each one of them will fall in a different location. And the X and Y coordinates are relative to the bullseye. So if you hit 0, 0, that would be a perfect bullseye. Okay. And if you don't hit one of the regions, that doesn't count. So we don't include those points. So here is the data. Let's actually plot it though. I'm really curious to plot it. So we'll plot dfx just like we did in the last time. Actually, let's just plot dfx first as a histogram, just like we did in the geyser eruptions. All right, we have a pretty different distribution here. It looks almost like a uniform distribution, but there actually are some peaks on the edges here. So, you know, you can kind of see that there are 3 categories, right? There's 1, 2, 3. Same if we did Y, I think it would look almost identical. Yeah, but let's actually try to plot dfx against dfy and see what we get. Scatter plot style. Okay, check that out. So this is our bullseye data. And you can see that we actually have 3 categories, right? 3 clusters. It's super obvious to your eye. Middle, second ring, and then outer ring. I guess maybe, you know, it's a bullseye board, right? Maybe one of those electronic ones. I don't know if any of you have any of you ever played bullseye, or played this game with your friends? It's really fun. I'm not much good at it though. Yeah, I'm exactly like you, Courtney. I'm very bad at it, but I like to play it though. So let's try to make a clustering algorithm out of this, right? So we can do the same thing as we did last time, where we do k-means, and we're gonna make a k-means object. And the only difference is gonna be that we're gonna try number of clusters equals 3, okay? Because we're pretty sure there's 3 clusters. And we'll do a random initialization. We'll make sure there's some maximum iterations. We'll use 300, just like we did for the last time. And we'll just hit enter. So now we'll try to fit, right? We'll try to fit this model. So we can use df.values to actually try to fit that. Remember, this is how we get the data into a list of lists, right? Which is what our algorithm loves to see. And then we will print out the flags. So let's just try that. Oh, forgot a comma. All right, so we get our classifications, and this time, oh, a little weird actually that we get only 2. That's interesting. Okay, we should actually be getting, oh, because I didn't say flags. That's from the last time. So sorry about that, everybody. I just got a little confused. So we have to actually redefine flags for our new case, because what we're looking at here is our Old Faithful geyser data. So we run that. And if we look at this, let me actually try to print this. Okay, it says we should set the value of n init, so I'm just going to do that. Okay, you get our data. I want to actually try and plot our data though. So we can see, okay, so there's actually 3 categories it chooses for us, 0, 1, and 2. But let's try and plot it in the same way that we did to visualize last time. So we'll start by defining the 3 categories. So we have category 0, and we're just going to use df flags equals 0. We have category 1 and category 2. So these are our 3 sources of data, right? And let's try to plot these. So we'll plot them just as we did last time. Plot the cluster centers, plot the data itself. I don't think we need these X and Y labels. I think we can just keep these empty, honestly. They're not really very informative. They're just X and Y. And so let's try this. All right, so here's our data. Not very promising, right? We have some clusters that are clearly not getting the picture here. They're not with the program. And why might this be? Well, remember, we have those assumptions, right? Spherical variance of our features, isotropic features, essentially blobs. And these are definitely not blobs, right? These are actually much more structured than blobs. So what we're going to do is we're actually going to use polar coordinate transformation. And I'm not sure if any of you remember from your math classes, but let me look up polar coordinates, and I'm going to show you what it looks like. All right, here's our polar coordinates. And basically, polar coordinates are converting a point that might be like on an XY plane, right? So it might have some XY values to a radius number, which is going to say how far away that point is from the origin. In this case, the origin is that bullseye. So how far away the point is from the bullseye is one thing we want. And then the angle, okay? So the angle would be like, is it towards the top, towards the bottom, towards any side or angle? So the way we convert, I believe there should be some kind of conversion here. Yeah, here's the conversion. So we're going to use the following conversion for transitioning from X and Y, okay? So let's actually implement this in our code. These equations, I know that they're kind of complicated equations, but don't worry, we'll cover them. We're going to implement them together, and you'll see that it's not as bad as you might think. So let's try this polar coordinate, and honestly, probably ChatGPT can help us. What did I say? It'll help us. So the first one here is converting R, making R, and the way we do that is we take the square root of the squared terms of the X and Y. And then theta is the angle, right? So R was that distance from the origin. Theta is that angle. And if we were to plot these again, theta and R, not X and Y, check this out, everybody. This is what we could call, let's put a title on here, because we want people, because it looks a little strange otherwise. Bullseye data set in polar coordinates, okay? So you can see we have our R and our theta dimensions. And we get these blobs. And so let's try to actually cluster again, okay? Let's try our clustering again because we now have blobs. We don't have bullseyes anymore. So we'll do another k-means model. Hopefully you're getting some practice with these k-means models. And we're going to fit and get our flags, categorize, and let's plot them. Okay, and we'll plot the cluster centers too. Give it a little label. Love that Copilot's helping us with this. Oh, and it seems like it didn't quite work this time. It's not liking our polar coordinate case. I might honestly just give it R and not give it theta. We probably don't need to give it theta. I'm not going to give it these either. Okay. I guess if we just give it R and not give it theta, it will work. Because if you think about it, theta, it doesn't need theta. Because, yeah, the theta is not really helping us discriminate between these. It's only the R that we care about. So now it perfectly clusters them. And let's go back and test and see if this actually works, if these clusters work. So we can do that by plotting category 0x and category 0y. Let's see if that works. Okay, great. Look at that. We got a whole category there. And let's try another one, and I'll print it in another color. Let's say orange. I don't remember which colors we used before. So we used blue for category 0, which we have here. We used orange for category 1. And for category 2, we used green. So, oh yeah, and then we can plot the cluster centers if we want. The cluster centers will all be the same though. So let's just not worry about that part. And we get our bullseye here. So yeah, congratulations. Now you are officially a k-means cluster. You did a great job going through this. And yeah, does anybody have any question about this k-means stuff? What it means, how we're doing it? So that's pretty much all we had for the day. Bullseye is colored in half instead of each circle on its own. So try this, Courtney. Try replacing the R, theta comma R. Just replace it with R. Okay. Just try to replace it with R. And I'm going to upload this to the GitHub. So let me do that right now, actually. So I've uploaded this to GitHub. So now if you go to GitHub, let me open that up actually, so you all can see. It's been updated. So you refresh the page and you'll see the code. And so if you run this exact code in your script, it should give you the right answer. So definitely give that a shot. And let me know what you think. But yeah, thank you everybody for joining. And let me actually give you all the link to the next stream, which is going to be our Today in Global Hack Week with Emily and Quinn. Okay, so the next stream is Today in Global Hack Week, and believe it or not, it's already day 5. Isn't that sad? Almost done. So just want to give you that stream link. But yeah, thank you all so much for joining today, and for all of your work on this. And yeah, let me know actually if you have any other questions. I'll stick around on the stream, and I can answer questions in the chat as we go fade away here. So yeah, thanks again, everybody. Okay, just going to come back for a quick encore here because Voip asked a question here. Don't know if you're still here, but how does the concept of stability apply to k-means clustering? Are there metrics to quantify stability of a clustering solution? Yeah, so that's what I was talking about with these this part of it. So we scroll up to here, and if your model is stable, it would mean that it's most likely going to have a centering around one inertia. So that's this part here. Now, if you didn't have a stable model, you would probably see an erratic distribution here of many different classifications. So hopefully that helps answer that question about the stability. Very good question. If we see many solutions happening and it's not just one solution that it settles on, you would see a lot of different inertia values here, not just clustering around one. So yeah, great question. But thanks everybody. And I guess we'll end it there now.